Now the first problem involved an object, mass 100 grams, that moves along an incline. Now the only information you were given is that as it moves along the incline from the start to the finish, its vertical position decreases by 80 centimeters. Okay, so we don't know what the direction of our displacement is. We don't even know if it's always in the same direction. We didn't say it's a straight incline. It could be any. It could have dips and humps. Could even have a little loop in it. There's only an initial position and a final position. And the only thing we know about the initial and final position is that they differ by negative 80 centimeters if you take upward to be the positive direction. Okay, well, whatever the displacement from here to here, if we take our displacement delta S and dot it with our gravitational force, what we're doing is we're taking the projection of the delta S in the direction of the gravitational force. Okay, there's our projection of F in the direction of the gravitational force, and multiplying it by our gravitational force. Okay, in other words, what we're doing is we're doing a dot product of delta S with the force of gravity, and when we do the dot product, we're multiplying or at least dotting the projections. Okay, why is that? Because whatever component of delta S is in this direction does no work in this direction because it's perpendicular to the direction of the force. Okay, so there's no work due to this component of the displacement because this component of the displacement is not in the direction of the force. Okay, so I set this up. I say our projection of delta S onto the gravitational force is negative 80 centimeters times the J vector, implicitly assuming, well, I made it explicit here. Y-axis is vertical, no angles given, might not even be a single angle of elevation. Okay, if we take this projection and dot it with the gravitational force, we're going to get the work done by the gravitational force. Okay, so another way to put it is we have delta x is delta S is some delta x times I plus some delta y times j. If we do gravitational force times delta x, we're going to have what? Negative m gj dotted with delta x plus delta yj. Well, that's going to be negative 80 centimeters times j. J, and it's delta x times I. J dot I is 0, okay, and negative mg dot negative mgj dot negative mgj dotted with negative 80 centimeters times j gives us this, and there's no j in it, and that equals what it equals. The delta x goes away. Alternatively, we can think of this projection and multiply this projection, and that's what I do here. Now, here's my m, here's my acceleration, so that's going to give me my negative mg, and times the negative 80 centimeters. We could do this in centimeters and grams and seconds, getting the work in ergs, but we don't really want to do that because that number is going to be really big. This is going to be in the order of 100,000, that's going to be in the order of 8 million. We don't want to think about a number that big. So we go to just SI units. express 100 grams as 0.1 kilograms, the acceleration of gravity in meters per second squared, and the 80 centimeters is 0.8 meters. And we get total of 0.8 Newton meters or 0.8 joules. Okay, so either way we want to look at it. If we want to look at the projection of delta S on Fgrav, or even the projection of Fgrav on delta S, and multiply the projection times the vector we projected on, we're going to get the result. And we're going to get the same thing we'd get if we just set everything up this way. And if we set it up this way, of course, we see clearly why delta x doesn't matter. It doesn't matter what the slope of this incline is. It doesn't even matter if it has a bunch of different slopes. The only thing that's going to matter is our change in the y-coordinate, which is negative 80 centimeters. If then the gravitational force is the only force acting on the object, its kinetic energy is going to change by 0.8 joules. So if it starts from rest, it'll end up with 0.8 joules of kinetic energy. You can figure out easily what the velocity of a 100-gram mass has to be in order to have 0.8 joules of kinetic energy. I think the square root of 8 meters per second, which is going to be about 2.7, closer to 2.8 or 2.9, 2.8 meters per second. You can easily work that out, but this is the thing you need to understand. If gravity is the only force acting, bottom line is only the motion in the y direction affects its kinetic energy.